All right, waves in one dimension. Now, I'm not going to lie, waves in grade 11 physics is supposed to be a huge, massive unit. And I don't understand why, because you don't do waves ever again. No, you don't see it in grade 12. This unit has zero impact on what you do in grade 12. And whenever you do need waves, you will probably forget whatever you learned here. So it's just like, what? Like, why are we supposed to spend hours and hours and hours and hours on waves? Granted, they can be pretty cool, but I always think kinematics and dynamics, those are the two main things that you need to know in physics. If you can't do kinematics and dynamics, you can't do physics. So waves, we do a little bit, sprinkle little introductions to kind of have an idea of what's going on, but it's not the huge deal moving forward into grade 12. We are probably, and I'm just going to veto it right now, Snell's law, kind of cool, but there's no time. So you're welcome. Okay. And this is even part one of waves. There's even another part two, like, yeah, bleh. So we're not going to do Snell's law. We're not going to have time. Really, all we're going to look at is we're going to look at wave properties and wave velocity. What does it mean to be a wave and how do waves move? And then we're going to look at reflection, interference, and standing waves. Maybe. Okay. Depending. Standing waves are way better to do in person. And then yeah. Okay, might talk about them for like a second or so. Really, this is just a very brief introduction. Waves, what is a wave? How does this all work? And good stuff like that. So you might say, Mr. C, I know what a wave is. I know what waves are. Ooh, wave, hey, hi, I don't know. Sort of, not really, okay? Waves, I'm going to kind of twist your understanding of waves right now, because waves are something that, yeah, you've seen before, you've dealt with, maybe you've learned about in the science class. But waves are transfers of energy through objects, okay? Waves is not some water going like this and passing you by. A wave is a transfer of energy, okay? And what's really different about how we look about waves now is waves carry energy, not matter, okay? And that might be a little bit weird to think about. If you think about a wave in the ocean, you might think that if you like pick one little like particle molecule of water and you watch that thing, you might think as the wave goes, that particle of water goes with the wave. But that's not true at all. The water pretty much stays right there. And as a wave passes through, it might go up and down, it might go side to side and oscillate a little bit, but that water is staying in a confined space. It's not really going anywhere. Current, if you have current in water, sure, that's a little bit different. But just a wave does not transfer matter. And that makes sense when you're dealing with a string. If I send a wave, this is going to be hard to see, but if I send a wave through this string, yeah, it doesn't really look like a wave, but if I send a wave through here, this piece of string over here is not moving over here, right? That's not happening. The energy of the wave is getting transferred to the string, but the actual physical matter of the wave is not moving. Okay, so that's why we think of waves as transferring energy. Okay, not matter, not actual particles, anything like that. Okay, so there are two different types of waves that we're really going to talk about. There are periodic waves, and then there's wave pulses. Okay, now if something's periodic, that means it comes back over and over and over and over and over again. And that a periodic wave is something that carries continuous energy from one place to another. Okay, so it's continuously going to an example of this here. Okay, I'm going to fix this end of the string right there. Over here, it's going to move, and I am continuously adding energy to this string to make a wave. Okay, I'm actually just moving it up and down there. That's kind of, string kind of sucks. But I am continuously adding adding energy to that string to make a periodic wave because it shows up over and over and over again. And what that would look like in picture form would be just a wave going like boo, 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 okay? And this wave is moving to the right, okay? Um, that is a periodic wave because it does not stop. A wave pulse is a single wave bump or packet of energy that moves through the wave. So wave pulse, it is a single bump and it's a packet of energy. And this might be really, really difficult to show on this string, right? Periodic wave never stop, but a wave pulse, I just make one go through, okay? It can happen once, sure, it could happen once, twice, 3 times in a row, but it is single packets of energy. It's just a pulse that shoots through the wave. I wish we were in person because slinkies and springs are really, really fantastic for this, but I just don't have that here, okay? And so a wave pulse, if we wanted to draw that in a picture, we've got our string, we send through a pulse and it goes like that, and this thing is moving again to the right, okay? Periodic wave versus a wave pulse. Think about it as like, it's hot outside, so maybe you're gonna go outside, you can grab your garden hose or something. When you turn on the garden hose, you got a continuous flow of water out the end of the garden hose. That is a periodic wave because it's a continuous flow of water. But let's say you screw on a little nozzle that has a little like squirt gun on it. So it stops the flow, but then you squeeze the handle and you go, psh, psh, and then you spray your sibling, psh, psh, or your parents, psh, psh, or your pet, maybe if you're evil like that. That is single wave packets. That is a wave pulse of water, a packet of energy that you are sending out. So we got 2 types of waves, but regardless of what we have, we need to be able to label a wave and know and talk about characteristics of a wave, okay? So this is a simple wave diagram. This is blah, 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 up and down, up and down, up and down. It's beautiful, okay? So there's a couple different things that we talk about. The first thing is how long the wave is, how wide, how long is this wave? And we call that, it is super, 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 it's kind of out there, so you might not have a hard time remembering it. It's called the wavelength. That is how long the wave is, okay? And that goes from one point to another because waves repeat. So this wavelength goes from, if we look at the top here, the top of the wave, we want to get right back to the same spot. So this thing goes all the way down, all the way back up to exactly the same point that it was, and that is one single wavelength. So a wave is made up of a whole bunch of individual wavelengths, okay? A wave pulse is just one little wavelength. That's it, okay? This is the wavelength of a wave pulse, right? It is just one single wave that is going by. Give me 1 second. I think my door is open and it's blowing in the wind. Give me 1 second. All right, we're back. We are back. Woo. Okay. Sorry. Everything's under control. Don't worry. So that is a wavelength. Okay. And we need a way to talk about kind of the different points of a wave, right? We've got this middle line, which we call the equilibrium line, but then we also have the top and the bottom. And what we call those, and again, you might have seen this before, but we call those, the top of the wave is called the crest of the wave, the very top, and the bottom of the wave is called the trough of the wave. I think that's how you spell trough. The trough of the wave, okay? It's just the top and the bottom. That's all it is. So in order to calculate the wavelength, you are going from one crest to another crest, or one trough to another trough. But it doesn't even have to be from crest to crest or trough to trough. It can literally be anywhere. We can look at right here. This point, right? Go up, down, come back to this point. That right there is also a wavelength. We can do the same thing over here. We can start here. We can go up, down, and come back to the exact same spot, that is also one complete wave. Those are all exactly the same distance called the wavelength. The very last thing is called the amplitude, and the amplitude is how tall the waves are, okay? How strong the waves are, essentially. And this amplitude, okay, is here, the amplitude, and the amplitude of the wave is always from the middle or equilibrium, okay? So this right here is our amplitude. We have another amplitude right here, right there, right there, okay? So it's not the full top to bottom, it's from the middle to the top. That is your amplitude, okay? Another word that you might see is a cycle. One wave cycle is just one complete oscillation of the wave. It's the same thing as a wavelength, but a cycle of the wave is when it does a full cycle, goes through start to end, okay? That's how we label a wave, characteristics of a wave. Beautiful, okay? Now, there are two more different types of waves, okay? There are different types how it transfers energy, okay? So yes, we have periodic and wave pulses, okay? But regardless, in both those periodic or wave pulse, okay, we can have two different types. We can have what's called a transverse wave or a longitudinal wave, okay? And it's really important to recognize here that waves don't move particles, right? I've said this before, it transfers energy. So these particles might actually vibrate and move slightly and bump into their neighbor. That is what transfers the energy through the medium, okay? And when I say medium, I just mean whatever the wave is moving through, whatever it's moving through. So you can have water, right? Water is the medium that a wave moves through. This string is the medium, the material that the wave moves through, okay? So two different types of waves. You've got transverse waves and you've got longitudinal waves. Transverse waves, the particles move perpendicular to the direction of energy transfer, okay? This is like water and this is like strings. This is also like when you go to a sports game, which don't exist anymore, but when they do exist and you go to a sports game and everybody does the wave and they go, wee, okay? That is a transverse wave. Because if we have a wave like this, okay, if we have a wave moving this way, like so, the particles are just going up and down. That's all they're doing. They're going perpendicular to the way that it's moving, up and down. The best way that I like to think about this is if you, oh no, where did you go? There we go. Right? You've got people here. Boom. Boom. They start to stand up taller, lift their hands up. Boom. I'm awful at drawing people. Boom. 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 This person's crouching very little, or they're just maybe a very little person. Then we can keep going up, boom, boom. You get the idea, right? If we were in class, I would make you do this, but yeah, it's not gonna happen. But that is a wave, right? When you see, if you've ever seen a sports game where the crowd starts to wave, you don't get people running around the stadium. I mean, you might because they're crazy, but you're not actually getting the wave created from people moving and running around laps of the stadium. You get people just doing this in their seats, and now you get a wave that goes from one side, like all the way around the stadium. That is a transverse wave, up and down, up and down. A longitudinal wave is a long wave, and that is the exact opposite, where the particles in the medium move parallel to the direction of energy transfer. This is how sound works, okay? And this is how it works if you're standing in line, or like if you're standing in line and somebody comes up and hits you and you go, bah, right? But let's say you're standing in line with a whole bunch of people and they go, bah, 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 and it moves through. that is a longitudinal wave because the particles are just vibrating like this back and forth, and they are not really moving anywhere. So I think I have a nice little video to show you. Come on. Waves. Do, 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 do. There's a nice GIF that oh, this is this one. Come on, you gonna load? You gonna load? Okay, here we go. This right here is a longitudinal wave, right? You see the wave moving through, which is great. I know it might be kind of choppy, but you see it moving through. But if you focus on one individual dot, like the red dot, or just pick any dot there, you'll see that that thing, those particles don't actually move anywhere. They're just moving parallel in the same direction as the energy transfer. In the bottom GIF there, you can actually see the wave. It follows a wave crest, kind of the front of the wave moving through the wave. That is a longitudinal wave. A transversal wave looks like this, right? Up and down. This is what I was talking about. Wee, wee, it's great, it's beautiful. If you watch one of those particles, just pick one, you see they're not actually moving. They're just going up and down. They're not going anywhere else. And that is a transversal or transverse wave. Good? Capiche? Good, good. I hope so. It's kind of mesmerizing too. All right. So, perfect. Okay. Longitudinal waves, we can say there's two parts of them. There's compressions and then there's rarefactions. I've never heard the word rarefaction before in my life, other than when I'm teaching this course. Compression, right? Particles are close together. Rarefaction is the opposite when they're spread apart. Okay. So if we go back to the picture, it's even labeled here actually. You can see the compressions and the rarefactions moving through on the bottom there. Compressions when the particles are squished together. Rarefactions are when they're spread out a little bit. Okay, cool. Just a little fun fact, really. Nothing too crazy there. Okay, so it looks like that. So we have waves, we have energy moving through particles. We want to know how fast does that energy transferred through the medium, right? How fast is this wave moving? And that is called wave velocity. Dun, 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 dun. Woo! You would have never guessed. Based on how much, like kind of where the source of the wave is and what the medium is, waves travel through mediums at completely different speeds, right? The same wave might move faster through something than it does in another thing. The speed of sound is much, I think it's bigger, it's greater in water than it is in air, or maybe it's the opposite. I don't remember. I can't remember. I just know sound travels better in water. But this waves travel differently in different mediums. So if we go back to our kinematics unit, okay, and we're just thinking about the speed of an object. Someone tosses in the chat, what does the speed of an object depend on? If we're going to calculate the speed, what does it depend on? Someone tosses in the chat. They're all probably asleep. That's fine. Distance and time. Yay! Woohoo! Right? Distance and time. Fantastic. Okay. Which means, what do you think the wave velocity depends on? Distance and time, maybe. Okay. But we don't deal with distances really, right? We've not really. But what we do deal with wavelengths, and the time for one cycle. So it's very, very similar, right? It depends on the wavelength, so how long these waves are, and how long it takes for a wave to do one complete cycle, one full up and down. How long does it take for that wave to happen? Okay. And what that formula looks like is this: V equals F lambda. Okay. Couple weird things. V velocity, that's totally fine. F is the frequency. This might be a new term, but this is the frequency of the wave. And I'm going to talk about frequency in a second. And this kind of Y, upside down Y thing, that is the wavelength of the wave. This thing is the Greek letter lambda. I think it's spelled like that, lambda. And it's like, if you want to draw it, it's literally like a curly upside down line and then give it another leg. Kind of like I don't even know what it looks like. It's like an upside down Y with a curl on the top. Okay. That's lambda. That is your wavelength. Okay. And so your wavelength is measured in meters because it's a distance, right? Your wave velocity is a velocity, so meters per second. The period or the frequency, okay, this is where things get a little weird, okay? Because frequency, we measure in something called hertz. And a hertz, an Hz, is per second. That is the unit. The unit is 1/second. So if I say something has a frequency of 5, okay, that means that this thing is happening 5 times per second. 5 per second, okay? That is what a frequency is. But frequency has a very, very, very close cousin called the period. And we talk about period as a capital T right here, and the period has units of just seconds. So the period is a time, and the frequency is the inverse of that 1/time. We don't say 1/s, we use hertz, we use Hz, okay? So those two things are related, and they are literally exactly the same thing. The frequency is just 1 over the period, and that means that the period is just 1 over the frequency, okay? So if you think about it, if I have something that has a frequency of 5, okay, 5 hertz, okay, we'll say this, 5 hertz. That's my frequency, okay? That means it's 5 times per second. The period is 1 over the frequency, which is 1/5, okay? So that is 0.2 seconds. And what that means is that it takes 0.2 seconds for one thing to happen. Because frequency and period doesn't necessarily have to relate to waves always, right? The frequency is just how often something happens. So if I have something with 5 hertz of a frequency, that means that something's happening 5 times every second, which means it takes whatever that thing is. Let's say I'm blinking 5 times a second. That's absurd. Can't do that. But 5 times a second, right? That means each individual blink is 1/5, which is 0.2 of a second. So it takes me 0.2 of a second, 0.2 of a second, 0.2 of a second, 0.2 of a second, 0.2 of a second. That's 5 blinks in 1 second. That's frequency and the period, which means we can relabel and rewrite this formula to be really exactly the same thing, but just lambda over the period. It's the exact same formula, but I just replaced the frequency with the period, okay? You can use whichever you want, it does not matter. But being able to read a question and recognize what's frequency and what's period, that is super, super important. So an example, one complete wave passes by a point in 0.2 seconds. What is the frequency of the wave? Okay, and we pretty much just did this question. If one full wave takes 0.2 seconds, okay? That is at the period or the frequency, okay? Period, one full thing, okay? Frequency, how many things in a second? So for one full thing, it takes 0.2 seconds, which means the period is 0.2 seconds. And if the period is 0.2 seconds, that means the frequency 1 over the period, 1 over 0.2, which is 5. If you want, you could do 5 per second, but that's per second, but that's really confusing. So we say 5 hertz. So it has a frequency of 5 hertz, okay? Super, super simple, similar. If a wave has a frequency of 60 hertz, so that's 60 times every single second. That's 60 times a second. So something is flashing on and off 60 times a second. Your lights, LED lights, turn on and off 60 times every second because that is the frequency of the electricity that's coming out of your wall right now. So 60 times a second, this thing's flashing on and off. The period, well, frequency, right? Anytime you see hertz, that means it's the frequency, 60 hertz. And that means that the period is just 1 over the frequency. So 1 over 60, which means it's 0.061 seconds. Okay? And that time, that 0.0617 is the time, the time for one complete wave to pass. Okay? Frequency and period. Super, super important that you can read and figure out the differences, because the rest of it is just a simple formula: velocity and your wavelength. Two things that are probably going to be given to you in the formula. But the frequency and the period is the thing that gets a little funky. So good stuff. Good stuff. Let's do some examples of wave velocity, okay? But before I do that, you know what's going to happen. I want to know, are you with me so far, or are you just oofing it? How are you feeling? Does this making any sense? Mm, 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 mm. Good. Okay, we're with me. We're good. So we'll fly through these examples and then we're good to go for the day. It'll be fantastic. So some examples, okay? The hardest part of these things is reading the question and figuring out what the information that they're giving you, okay? So a person standing in the ocean is timing waves as they pass by, because you know what? That's what every person should do when they go to the ocean. That just makes sense, right? Not lie on the beach, not go enjoy the waves, go enjoy the sun or whatever. No, you're gonna sit there, you have a stopwatch, and you're gonna time the waves as they go past you. So they noticed that 10 waves pass by in a span of 100 seconds. They also noticed that the waves have an average wavelength of 2 meters. So it is 2 meters as these waves go, that is a 2-meter distance. So frequency of the waves. Now, again, reading comprehension here in physics, super important. What is the frequency of the wave? So it's not good enough to say 10 waves in 100 seconds, right? That doesn't mean anything. But what that means is that it takes in 1 second, or sorry, not in 1 second, there is one wave every 10 seconds, okay? One wave every 10 seconds. Is that the frequency or the period? Okay, remember, frequency per second, how many times it happens per second, versus the period being the time for one full thing. So if one full wave goes every 10 seconds, then that means that the period of these waves is 10 seconds. It takes 10 seconds for a wave to go by. And if you've ever been like, right, water waves are pretty slow most of the time. They just kind of go, they just kind of saunter on. So if the period is 10 seconds, then that tells me that the frequency is 1 over the period, which is 1 over 10, which is 0.1 hertz. 10% of a wave will pass by every second. It takes 10 seconds for one full wave to go, okay? And now that we have a frequency and their period, finding the velocity, super simple. It's just some plug and chug, right? The velocity, you can use either formula. It don't matter, whichever one floats your boat better. So I don't know. I'll do, sure, it's right there. Lambda is a 2 meter wavelength divided by 10 seconds, right? Which is 0.2 meters per second. So these waves are moving at 0.2 meters every second as they saunter through the water. It's beautiful, beautiful, good stuff. Okay, awesome. Next one, radio, because the radio still exists. Did you know that? I didn't know that. I thought that radio was dead, but radio still exists. So CBC broadcasts radio on AM radio at a frequency of 990. Okay, right? If you think about when you go to your dial and you twist it, and if you go to CBC, maybe you go to Hot 103. That's FM though, but right, Hot 103, Country 104, whatever it is. That corresponds to a frequency. So when you are at 990 for CBC radio, that is a frequency of 990 kilohertz. Okay, frequency 990 kilohertz. And if we think back to our very, very first unit, a kilo is times 10 to the 3. So it is times 10 to the 3 hertz. Okay, little fun fact, AM radio. Does anybody know what AM stands for versus FM? Anybody? I appreciate the honesty. Have you even heard of AM radio and FM radio? Someone please tell me that you've heard of radio. Okay, good. Phew. AM, amplitude modulation. Yes. Okay. You definitely knew that. Absolutely, you did. You did not look that up at all. You're correct. AM stands for amplitude modulation. Modulation essentially just means changes, okay? So if we think back to our picture of the wave, everything about this wave stays the same except for the amplitude. This amplitude gets modulated, gets changed up and down as the wave gets broadcast. And that's how it sends information through the wave, is by changing what the amplitude is. If you've got louder stuff, you have bigger amplitude. FM radio is frequency modulated, okay? Which means the frequency changes, and that's how they send information. So they change how fast, like if I'm making a wave, let's say we're listening to some music, right? And the music's pretty steady, and so here's my frequency, and then the bass is about to drop, get ready, and then it goes back down, builds it up, bass drop, right? That is a frequency modulated wave, and that's how information is sent through those waves. So this question specifically, we have to do AM radio because we can't have modulated frequencies, because then the question just doesn't make sense, okay? Regardless, AM radio has a frequency of that, and it's a radio signal, which means it travels at the speed of light, and the speed of light is measured by a c, okay? I don't know why. I don't know. It just is, okay? It is. It's C, it's 3 times 10 to the 8 meters per second. It's super fast. Okay. So what is the wavelength of these waves? Okay. So if we know here, and this might seem a little bit like chemistry maybe, because I think you do some of this stuff in chemistry, right? The wavelength or the velocity is the wavelength times our frequency. Okay. We want to know what the wavelength is. So the wavelength is just our velocity divided by our frequency. We could do this with the period too if we really wanted to, but we have our frequency, so might as well, which means this is just 3 times 10 to the 8 meters divided by, or sorry, meters per second divided by 990 times 10 to the 3. You plug and chug that, you get 303 meters. It's a wavelength, so it must be a distance, okay? 303 meters. Oh no, sorry if that was loud. 303 meters. That is huge, okay? And that is why, if you've ever been listening to the radio, maybe you've listened to the Jets games on AM radio, and you go downtown, it might start to get fuzzier, it might start to break up. Because these are huge wavelengths, that those big buildings downtown cause interference because these wavelengths are huge. It takes 300 meters for one of those waves to do complete cycle. So if you could imagine, you could visualize that, you could see these massive 300-meter waves flying through the air. That would be crazy. You can't see that though, but it'd be pretty cool. Other things have tiny wavelengths. So big buildings like that don't bother them because they go up and down, okay? Cool, fun stuff, okay? Next time you listen to the radio, that's your homework for tonight. Listen to the radio and think, oh, look at that wave. It's 300 meters long coming into my radio. It's beautiful. Okay, last one, porpoises. Gotta love a good porpoise. I don't even know what a porpoise is. Isn't it a dolphin? Anybody know? I don't know. Is it a dolphin? Special type of dolphin? Same as a dolphin? Not a dolphin at all? Kind of looks like a dolphin. Anybody know? No? No one's gonna call me out, say I'm wrong? No? Have you just tuned me out now because I'm annoying today? I get it. Totally get it. So, fun part though, porpoises use sound waves in order to navigate, right? I believe this is called echolocation. They send stuff out, they figure out where things are, and then they can navigate through the water, which is fantastic. So thank you. It's a type of dolphin, porpoises, porpoise the dolphin. So they use sound waves that are 2.5 centimeters long, tiny, teeny tiny compared to the massive radio waves that our radio signals are sent through, which makes sense. Why would a little porpoise send out a 300-meter long wave? That makes zero sense. It's going to send out a little tiny wave that goes through, okay? And in water, sound travels at 1,470 meters per second. So yes, I was correct. Sound waves travel much faster in water as a medium versus air. In air, sound travels at 343 meters per second. But in water, it's like 4 times as fast, okay? So what is the period of these sound waves? That's a great question. Let's figure it out. We know the wavelength, 2.5 centimeters. Okay, we don't really like centimeters. So let's go to 0.25 meters. There we go. Oh no, it's frozen again. Just when I was on a roll. What a bummer. Mood killer. Unbelievable. Okay. 2.5 centimeters, whatever. It's like 0.025 meters. That's fantastic. Okay. We know the velocity. These things are moving at 1,470 meters per second. That's super fast, okay? What is the period of these sound waves? Well, if we want to find the period, we should probably use the formula that involves period. Wavelength divided by the period, which means the period is just going to be the wavelength divided by the velocity, how fast they're going. This is just a nice simple formula. This is easy peasy compared to what we were doing before, 0.025 divided by how fast it's going, 1,470, which means this thing has a period of, I had the answer on my screen, now it's gone, 1.7 times 10 to the negative 5 seconds, okay? And remember, that is a period. So it has units of seconds, and that is the time for one single wave to happen, okay? That is a tiny, tiny time. And if you have a tiny, tiny small time for one wave to happen, that means you're gonna have a massive amount of waves happening in 1 second. So the frequency being 1 over the period, just being 1 over 1.7 times 10 to the negative 5, that gives you something like 58,800 hertz. That is a huge number. That is saying that every second, 58,800 waves leave the water porcupine, the porpoise. How do you spell it? Porpoise. Okay, that is ridiculous. There's a ton of them, but does it make sense? Yes, because in order for this thing to see and move around in the water, you'd expect for it to be sending out waves, a ton of waves all the time, so it knows exactly where it is. As this porpoise dolphin thing is swimming through the water, if it's only sending out a wave like, I don't know, once every second, well, it's going to travel pretty far in 1 second. It might hit something. So it's got to send stuff out super, 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 super quickly so that it knows it can update its information really, really fast. Okay. That would be like trying to drive a car, but keeping your eyes closed for a second, then opening them for half a second, closing them for a second, opening them for a second, closing them for a second. Like, no, that's a recipe for disaster. It's how I drive, but it's a terrible idea. Don't do that. Okay. And that are wave examples. Okay. So you have a nice, beautiful worksheet right here with all the answers there. Just nice using the formula. Nothing too fancy here. You can try some practice questions. The quest is mostly just stuff like this. So if this makes sense, if you're following with me, that is just pretty much what all the quest is.